All right, today we are going to be looking at the structure of the atomic nucleus. So the nucleus of an atom has two main components to it. First is the neutron, shown here in blue. And then we also have the proton. Now these protons and neutrons, they are collected kind of together into the core of the atom. We're just going to signify it with this little orbital with electrons that kind of not necessarily float, but orbit around the nucleus of the atom. They're too high in energy for it to be a part of the nucleus, and it's a little bit beyond what we're actually going to be talking about today for this recording, so we're just going to leave those be for today. Now the neutron has a zero charge, whereas the proton has a positive 1 charge. These charges are due to small particles that are called quarks. These quarks are very, very small particles. They're actually fundamental. So in other words, you can't break these down. They're a fundamental state of matter, and they have a spin and a charge to them. Now, if a quark has a positive charge or upward spin, as signified by the arrow, the charge will be 2/3 charge, which is rather interesting. Now, quarks can also have a negative charge or a negative 1/3 charge with a downward spin. This is very interesting because it can help determine why neutrons have a charge of 0 and a proton has a charge of 1. We can do a little bit of math and look at it. So neutrons contain 1 up quark and 2 down quarks. So when we put this math together, we got a positive 2/3 charge minus 1/3 minus another 1/3. So we can take these two together and get 2/3 minus 2/3, which equals 0/3, and that leaves us with 0. This is why neutrons have a charge of 0. Now let's look at the proton. I'll leave this information about neutrons up still because I find that rather helpful information. All right. Now for protons are the opposite. Protons have 2 quarks that are in the positive or upward direction, or an upward spin, and they have 1 quark with a downward spin. So when we do the math on this, we got 2/3 positive plus another 2/3 for the 2 quarks that are going up, and then 1 quark going down, which would be a negative 1/3. So let's put these two together. So that equals 4/3 minus the 1/3 that's remaining, which leaves us with 3/3, or in other words, 1 positive, which is where we get the positive charge on the proton. Now this is fascinating and interesting because this is what helps determine why are protons and neutrons the charges that they're at. In addition, I've always wondered, why is it that neutrons and protons are even able to clump together? Because as we know, since neutrons are a 0 and protons have a positive 1 charge, you would think that because of the positive 1 charge on the proton that it would repel, so then the protons couldn't even stick with the neutrons. Rather, as I used to think of it, just float around with possibly the electrons just out into orbit. This is due to a force called strong nuclear force. Now, there are 4 different fundamental types of forces. And I'm going to put them in increasing strength. So the first one is the strong nuclear force. The second is electromagnetic force. And an example of this would be the repulsion of the protons. And this does actually happen. This is a real thing that does occur, except because the strong nuclear force is stronger in charge, it's able to overcome the electromagnetic force and keep them more boundly close together. Now the third one is the weak force, and the fourth is gravity. And that, once again, this is increasing in force as we are going up. The strong nuclear force is able to overcome the electromagnetic force only at very, very short, small distances. In fact, at 1 × 10⁻15 meters, which is extremely small. That's how small it needs to be in order for the protons to not repulse each other and rather become attracted to each other through this strong nuclear force. Now, my favorite example of this is actually the sun. See, as the sun that we have here, just draw a little sun right here, make it nice and cute. Now, as the sun, as we know, is filled with hydrogen and helium atoms, these hydrogen and helium atoms are extremely closely packed due to the high energy of the sun and to lots of pressure. Now, as these atoms are really, really close together due to the high energy between the two hydrogen atoms and the helium atoms, they're able to become fused together through a process called fusion. This actually occurs through the strong nuclear force. If it wasn't for that, we wouldn't have the sun. As these atoms come closer together through the strong nuclear force, energy is emitted during this process, and that is what actually radiates off heat to warm our Earth. All right, I would also like to talk about the periodic table of elements. So as we can see here, for each element, there are 2 different numbers basically attached to it. The top number, as demonstrated by up here in the example that I'm highlighting, the top number is called the atomic number. Now, the atomic number represents the number of protons contained within each element. Now, if we go down here to potassium, calcium, and going across this direction, notice that we increase from 19 to 20 to 21 protons in each atom. So as the number of protons increases, it's what actually is changing what the atom is, which is really cool. And it's very helpful as well as we look at the periodic table to understand this trend, so that we can read it a little bit more simply. And we can even see that starting from hydrogen over onto the very left-hand corner of the table to the helium atom on the very right-hand side. Now also, there's a second thing that we like to look at, and it's the bottom number, and that is the atomic weight. Now, the atomic weight consists of the total number of protons and neutrons within an atom. Now, this is extremely helpful, as from understanding the number of protons shown from the top number and comparing it with the amount from the atomic weight from the bottom number, we're able to determine how many neutrons are within an atom as well. So, as an example, let's look at sodium. Now, sodium, Na, has a total of 11 atomic number, or essentially protons. Now, sodium also has the number 23 as its atomic weight. Atomic weight is measured in atomic mass units. So, to calculate the number of neutrons, we will take the atomic weight and subtract it from the atomic number. So, we have 23 as the atomic weight, minus 11, the atomic number, which will give us 12 neutrons total. This helps us read the periodic table of elements. Hopefully this helps you out. Next, we're going to quickly discuss who helped in determining and discovering the structure and nature of the atom and its atomic nucleus. Now, there have been many scientists who have helped us understand the nucleus and the structure of the atom. For example, there's Rutherford, Democritus, Niels Bohr. We're just going to focus on these two today. Democritus was a Greek philosopher who lived in 400 BC, and he proposed the theory of the universe. And he also coined the term atom, which came from the word atomus, which meant indivisible. Now, he thought if you took matter and divided it more and more, eventually you would get to a point where it can no longer be divided. Now, this last final division he called the atom. He considered that the atom would be completely solid, it had no real structure, and had a different mass, size, and weight and shape to each individual atom. But most important, he deduced that all matter consisted of atoms. This was his theory of the universe. Now, there are many things that are wrong with it, such as we know that the atom isn't completely solid. It does have actually a lot of space because of the distance between the nucleus and the electrons. However, this was very fundamental. This is new knowledge. Back in 400 BC, we're still learning things about the structure of an atom. It wasn't until, the 1900s when we really started to understand it. So, for example, Niels Bohr, he lived in the 1900s, so 1910s, and he created the Bohr model. From the Bohr model, it exhibits many perfect, or not perfect, but really great qualities of the nucleus and the structure of an atom. It's a very basic, simplistic way to view it, but it's a lot improved from what it had been in the past. He deduced that the electrons orbited the nucleus. This can be seen in the diagram shown over here at level 1, level 2, and level 3. He indicates that electrons are able to not fall into the nucleus, as we discussed earlier, because they have high energy states. These higher energy states are because of these different levels. So, for example, the further away you get from the nucleus, or the higher level you are, the more energy that electron would contain. So, level 2 electrons have higher energy than level 1. Now, this also was a big breakthrough in the structure of the atom. However, it does also have its limitations. The structure in the model, this Bohr model that he has here, shows as though the electron is only orbiting almost in a planetary fashion. We know that this isn't quite correct. Electrons kind of move in almost any direction within the level, so it can be on the X, Y, or Z axes of their orbit, not just in this kind of two-dimensional rotation. But these are two amazing scientists who helped us understand it more. But overall, this is the structure of the atom and of the nucleus. Thank you so much for listening. I hope it helped understand a little bit more about what neutrons, protons are, how we got their charge, how we're able to determine and understand the periodic table a little bit more, as well as some of the people who have had a great influence on our understanding and the structure of the atom.